Yeah. Ask the operator. They're saying that they couldn't find the lecture on Monday online. Did you find other lectures online? Yeah. Could you please check that? Thank you. That's pretty important because you need that lecture for the assignment that's due on Friday. Okay. Let me start with a couple of announcements. There's homework number 2 is due on Friday. It's on Z-transforms. Just a quick show of hand. How many people have already done it? Finished. Okay. And how long did it take on average? Did it take more than 10 hours? Good. What? Is that surprising? Does it normally take more than 10 hours? No. Yeah. 3 hours. Beautiful. The second announcement is that there's no lecture on the 17th and 19th. I've already announced that a bunch of times. There will be a makeup lecture on September 29th. And the makeup lecture we had on Monday is already online for those of you who missed it. What happened to our class? Are people watching the videos, or nobody knows? Well, those of you who are here obviously aren't watching the video, so that's a dumb question. But there's also an interesting division. It's like 2 columns where nobody sits right in front of me. You probably want to just avoid eye contact with the instructor at all costs. Ah, the videos are over there. Okay, the video is better than me. Okay. It is, because the writings are on the videos, not on my face. Okay, good. I'm glad you explained that. I thought maybe you're doing some illegal thing and you don't want me to be watching like I don't know, under the table or something. But no, none of that. You're reading the newspaper, eating burritos, all the things I don't like. Okay, so are there any questions or comments? All right, so what we're going to talk about today is sampling. That's chapter 4 of Oppenheimer and Schaefer. To some extent, we already talked about sampling. We talked about, I'll give a quick sort of a pictorial overview of the kinds of things we talked about. Just the basic Nyquist sampling, what happens to the spectrum of the signal when you sample it, and what aliasing means, and under what condition you can get your signal back and all that. We also talked a little bit about downsampling, and we had those diagrams that those pictorially that showed you what the spectrum of the signal, what happens to the spectrum of the signal when you downsample something. Today I'll talk about upsampling just a little bit. Then I'll talk about changing the sampling rate by a non-integer factor. And then after that, I'll talk a little bit about how you would use a discrete time system, like an LTI system, to process a continuous time signal using sampling. And I think that'll be the end of today's lecture. And then on Friday, I'll talk a little bit more about multi-rate signal processing, followed by moving on to the next chapter, which is difference equations and IIR filters and flow graphs and stuff like that. Okay. So let me just refresh your mind real quickly about the concept of spectrum and what happens when you do sample things. So this is just a 4-minute overview. Could you zoom in on this sheet here? Great. So what we talked about, I think 2 or 3 lectures ago, was if you have a continuous time signal, you multiply it by a train of delta functions spaced t apart, and then you convert that train of delta function, which is still a continuous time signal, to a discrete time signal by just I guess, integrating the area and then each delta and figuring out the area will determine the value of x of n at that point. Then the question was, how is this spectrum, the continuous time Fourier transform of this guy related to the continuous time Fourier transform of this signal? And we had these diagrams here. This is a time domain. That's the spectrum in the time domain. This is a train of delta function t seconds apart. This is the spectrum of a train of delta function. You multiply these two things, you get a train of delta function. It corresponds to convolving these two things, you get these things. And then once you have this x of s of omega, which is the Fourier transform of this signal here, then converting it to x of n, a discrete time signal, which would mean integrating the height, the area underneath each of these deltas will become the height of x of n at this point. That process, it results in the spectrum of this to get converted to that, where the capital omega for continuous time Fourier transform gets translated into little omega. And all that happens is that this line, this axis, gets scaled by a factor of t. So whatever that was 2 pi over t just becomes 2 pi. Just change the labels here, multiply all the labels by t, and boom, you got your answer. Okay? So that led us to the idea that, if this signal was if omega c was smaller than pi over t, then if omega c was exactly equal to pi over t, that corresponds to the case where we're critically sampling this thing, and therefore in the discrete time spectrum, these spectrums are just barely touching each other at pi. So if you sample this signal at t such that omega c is pi over t, in the discrete time domain, they just be touching each other at pi. You have a question?
I was just curious at what point did that discrete time signal become continuous time again, so you could take the continuous time Fourier transform?
What do you mean, at what point?
Well, I mean, like you sample it and you have these, just like a vector of numbers.
Yeah.
And then
This is it. That's the vector of numbers, x of n.
okay. And then you said you wanted to look at its continuous time Fourier transform.
No, it's discrete time Fourier transform. Maybe I did say continuous, but that was a slip. So this is the discrete time Fourier transform of that. This is the continuous time Fourier transform of that. You have continuous time Fourier transform for continuous time signals and discrete time Fourier transform for discrete time signals. So this picture you've already seen in 20 and 120 and also once again here. And so the idea is that if I just sample this at fast enough, not too much, not too fast and not too slow, that's called critically sampling it. Then the pieces of the spectrum here just barely touch each other at pi. So if I sample this at t equals pi over omega c, or let's see. Yeah, pi over omega c, then I get this picture where they're barely touching each other. If I sample it at a higher rate, then these things won't be touching each other. If I sample at a lower rate, they'll be aliasing. So then the next set of pictures I introduced last time was for downsampling. And let me just, for convenience, switch to Oppenheim and Schaefer here. And show instead of showing my own hand-drawn pictures, there's much better, beautifully drawn pictures in Chapter 4 of Oppenheim and Schaefer. So if I downsample, now, first of all, what does downsampling mean? Let's just show that here. What it means that you start with this signal x of n, and you throw away. Let's say if I downsample by a factor of 2, I throw away every other samples, and I get. If here I had A, B, C, D, E, I get A, C, E, etc. And how does the Fourier transform of discrete time Fourier transform of this downsample signal related to discrete time Fourier transform of this upsample, the normal signal, not upsample? In other words, what happens to the discrete time Fourier transform when you downsample? That's what we're sort of after. And the pictures are as follows. I already drew it in the last lecture, but this is merely a reminder. Okay, so if you can zoom in as much as you can into this page, great. So you start with the continuous x sub c of omega. This is a continuous time Fourier transform of the signal. We're assuming it's band limited to omega sub n and minus omega sub n. And then what happens is, well, I'll move on to this third plot. This is x of what I call x of omega. After I sample this top signal, can we zoom out just a tiny bit so this and this can be shown? Great. So if I sample this signal at rate t, the Fourier transform of it would look like this. Capital omega got converted to little omega, and all that happened is the labels of my things got multiplied by t. Okay? If there's one thing you remember at the end of this course, till you turn old and die or whatever, is this. If the continuous time signal had axes, was band limited to this, you sample it by t, this is the capital omega turns into little omega, and this gets multiplied by t. Just intuitively, that's all you have to remember. When you do the exam, when you do the homework, that's the relationship between these two things. And then the next step that we showed last time was that now if I subsampled this signal by a factor of 2, what happens to its Fourier transform is it's half of x of omega over 2 plus x of omega minus 2 pi over 2. We derived that in the last time's lecture, or a couple of lectures ago. And what that does, it's a couple of steps. I'm not showing it here, but what that does, it sort of spreads, it fattens up these guys, and it spreads it. And the picture we had for that was, zoom back, please. So this was x of omega. This is x of omega over 2. This is x of omega minus 2 pi over 2. You add this guy and these two spectrums, and you get that. And that's exactly why we have this. Okay. And so that's really what happens to the spectrum of signal. And so what's the lesson that we learned? And it was sort of at the very end of a couple of lectures ago. What's the lesson that we learned from these pictures? Well, the lesson that you learn is that, again, when you downsample this spectrum, this original spectrum, can you zoom out just a little bit so that this is included? So when you downsample this discrete time signal to get that, this thing gets spread out. And if it didn't have enough, if it wasn't sampled at a high enough rate, okay, then what happens is these things could potentially spill over and produce aliasing. And is that understandable? Yeah. If you start with a signal that was not oversampled, it was just, let's say, critically sampled, now from that critically sampled, you get rid of some of the samples. Now you become undersampled, and therefore you expect to get aliasing. And so if I started with this signal and this M guy, if either this spectrum was fatter, then these things would spill over, and I'll have aliasing. So when you do downsampling, you have to prevent aliasing by first low-pass filtering and then downsampling. An example of that is shown here, where aliasing does occur, or you could prevent it from happening. Again, zoom in. That's the continuous time signal ranging from minus omega n to plus omega n. We sample it at some rate, and it's now between minus pi over 2 and pi. And now we subsample this thing by a factor of 3 instead of by a factor of 2. It doesn't even have to be that this thing was fatter, but let's say we subsample by a factor of 3. Now, will this sustain itself? No, because here we've only oversampled by a factor of 2. It only goes all the way to pi over 2 rather than pi. If this thing was touching pi, it would have been critically sampled. Now that it's touching pi over 2, we've only oversampled by a factor of 2. But now if I downsample by a factor of 3, I'm going to go below critically sampled, and this is the spectrum that I get. And that's the aliasing. And how is this spectrum related to that? It's this equation that we derived a couple of lectures ago. It's this thing. 1 over m, I equals 0, m minus 1 of that, where in this case m is 3. So so there's 3 terms in this summation, and that's sort of zoom in again. And that's the thing that you would have gotten. And that's where the aliasing happens. And this is much worse than if you can prevent worse problems if you just ahead of time low-pass filter your discrete time signal using it as some sort of a low-pass filter, and then do the downsampling by a factor of 3. Then you get something like that. where you have less you lost some of your signal, you've lost the highest frequency stuff, but at least the highest frequency stuff is not folding over to destroy and pollute the low frequency portion of your signal. So then that's what you end up getting. Okay? So I want you to be very comfortable with these pictorial manipulations of the spectrum. When I sample by T, the thing gets stretched by T. When I downsample, it's the summation of those three terms, and figure out what happens to the spectrums and all. So this is all review of downsampling, and we've covered that. The thing you have to remember is when you downsample, if the original signal wasn't oversampled enough, when you downsample, you get aliasing, so you better low-pass filter it before you downsample. So what I'm going to talk about, so then the block diagram, if you will, of a system that does downsampling is this. You start with a discrete time signal. If you want to downsample by a factor of m, you always low-pass filter it with a low-pass filter of ideal cutoff frequency pi over m to make sure that when you downsample, things don't spill over and touch each other. Okay, so to make sure that the high frequency portion doesn't alias over and destroy the low frequency stuff, right? So why is it that it's pi over m? Well, again, if you have this thing here, if you're going to be subsampling by a factor of 3, it turns out pi over 3, for example, is the exact low-pass filter you have to use to band limit this original signal in this form, so that you don't get aliasing. Okay. So this is more or less all review. What I'm going to talk about now is upsampling, which is the opposite of downsampling. Let's come back here. These pens seem to work very well. No. I got a brand new one. Oh, not that. Yeah, use that. Okay. So upsampling. So what does upsampling mean? It's the opposite of downsampling. When you were downsampling, you threw away, let's say, 1 out of every 2 samples. When you're upsampling, you add a new sample. Let's say upsampling by a factor of 2, you add 1 new sample for every old sample there was. If you're upsampling by a factor of 3, you add 2 new samples for every old sample that there was. So that essentially upsampling corresponds to increasing the sampling rate by an integer factor. So you start with x sub c of t, and you've sampled it at rate t, and you've already got a discrete time signal x of n, which is a sampled version of the continuous time signal. But you realize that the thing that you got is you wanted to have more samples. What does it mean? Let's say you use your digital camera and you set the number of pixels that you get by 200 by 200. You got the picture, you put it in your computer, and then you said, I wanted it to be bigger. I wanted to occupy a 400 by 400 pixel region in my screen, for example. That's the process of upsampling, right? There you're upsampling by a factor of 2 in the x direction and a factor of 2 in the y dimension. Or you've sampled the audio signal at 8 kilohertz, and you say, I really wish I'd sampled it at 16 kilohertz. I want a 16 kilohertz version of this, for whatever technical reason. Maybe the device that plays it needs it at that rate. Maybe some other reason you want to be able to send it to your friend who has a 16 kilohertz player or whatever. And so there what you really wanted to have is to have sampled it at t over L and gotten a different signal, x sub I of n, where I here stands for interpolated, which is x sub c of nt over L. So pictorially, this is your continuous time signal. Initially, to get this guy, you sampled at this rate. And so that would have given you x of n. And then later on, you decided, no, you wanted more. So you wanted to have, let's say, these samples as well in between. Okay. So the question is, can I possibly obtain x of I from x of n? And what do you think the answer is? Intuitively, can we? We have to invent new samples. We have to invent these red guys. Can we ideally do it? I mean, suppose you had a real continuous time signal, let's say my voice. You sampled it at 8 kilohertz, and then tomorrow you said, I wish I sampled it at 16. Can we really do it?
No.
Yeah, strictly speaking, no. Why?
It's not random. If we know that there's X of n has been sampled at twice the frequency, the cutoff frequency,
Uh-huh.
we should be able to reconstruct it.
You mean you should be able to get xi? That's exactly right. The answer is, it depends whether t was fast enough for the continuous time signal that we had before. If x of n was a sampled version of x of t at a high enough sampling rate, Nyquist rate or higher, then theoretically speaking, from x of n you can go to x of c. You can actually reconstruct x of c, the continuous time signal, right? That's what Nyquist tells you to do. If you've sampled fast enough, you're going to get back the original time domain signal. So if the answer is, if I had sampled this thing fast enough, I can get x of c, and then, again, theoretically, I could, once I reconstruct x of c, then I can sample it at twice the rate or 3 times the rate and get x of I. On the other hand, if in the process of going from here to here, I lost some information, then that information is gone, gone, gone forever, and I can't faithfully reconstruct x of c, and therefore from x of c, I can't faithfully reconstruct x of I. Okay? So the answer is, could you show me half the picture? Great, thank you. The answer is, it depends. If x of c of t was sampled, I put it in code, fast enough to obtain x of n, then the answer is yes. We could do it. So let's plot some pictures here again. So if your x of c of omega is band limited to minus omega n plus omega n, and suppose I sampled to get x of omega, which is the discrete time Fourier transform of x of n, by sampling at t. So suppose I sampled it so that the spectrum now looks like this. This is pi. Then it's pretty much critically sampled, and this is equal to omega n times t, for example. Then all that's happening. So that's ideally speaking, that's the discrete time Fourier transform of that. And what would be the discrete time Fourier transform of x sub I? This guy. Well, how is it related to x sub c? Well, it's x sub c sampled at t over L. So it'll be the same thing. where I get, so this is x sub I of omega, which is the discrete time Fourier transform of x sub I of n. It's the same guy, but it's sampled at t over L. So multiply this by omega n t over L, which in this case, because it was pi, it's pi over L. So the spectrum of this guy is, these three things are related sort of in this manner. Okay? So other than the complicated way of going from here to here and then upsampling from, and then sampling this properly going from here to here, is there a shortcut whereby I can go from this spectrum to this spectrum directly? And the answer is yes, and that I'll propose a system that does that, and then I'll show you, prove to you that that system accomplishes what we want it to do. Okay? So the proposed solution to go from x of omega to x sub I of omega. I want to arrive at x sub I of omega from just having x of omega, or start from x of n and arrive at x sub I of n. Here's what I do. I start with x of n, and I'll upsample it by a factor of L, and I get a new signal that I call x sub E of n, and then I'll low-pass filter this thing with a filter that has gain L and cutoff frequency of pi over L to get x sub I of n. That's my proposed system. And let's see if it does what we want it to do. So you start, what do I mean by upsampling by factor of L there? I mean that x sub E of n, by definition, is given by x of n over L for n equals 0 plus or minus L plus or minus 2L, da 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 da, and it's 0 otherwise. So how does x sub E of n look like? Well, if x of n, let's draw some pictures here. If x of n looks like, well, if let me draw some x sub c of t first. So if x of c of t looks something like this, where the samples are let's say are A, B, C, D, E, F, G, and these samples are t seconds apart. And remember, our goal is to get x sub I of n. So this thing, A, B, C, D, E, F, G, that's our signal x of n. And the x sub I of n is D, D prime, E, E prime, F, F prime, G, G prime, C, C prime, B, B prime, and A prime. So A prime, B, B prime, C, C prime, da 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 da. That corresponds to x sub I of n. Okay. So pictorially, I want to show you what x sub E of n looks like. Well, if this is a continuous time signal, x of n as a function of time would look something like this. So these guys are t over 2 apart. So x of n will have the signals, what, D, E, F, G, A, B, C. It'll have, yeah, 0, minus 1, minus 2, minus 3, minus 4, 1, 2, 3, 4. It'll have, this is 0, 1, 2, 3. So at minus 3 it has A, then it has B, then it has C, then it has D, then it has E, F, G, etc. Okay? And x sub I of n what would it have? It'll have, again, samples 0, let's see, -1, -2, -3, -4, -5, -6, -7. It'll have, at 0, it still has D. At -1, it has C prime, C, B prime, B, A prime, A, and then 1, 2, 3, 4, 5, 6, and it'll have D, D prime, E, E prime, F, F prime, G, G prime, etc. So that's an X of n and X of I of n. And what is X of E of n, the thing I just proposed to produce? Well, that will then have X of n, but zeros in between. So it'll have 0, -1, -2, -3, -4, -5, -6. So this is X of E of n, the intermediate signal in this system that I've proposed. And it says that it's at time 0, it takes on the value D. At time 1, it takes on the value, it pretty much looks like this, but zeros in between, okay? At time 1, it takes on the value 0. Time 2, it'll be E. At time 3, it'll be 0. At time 4, it'll be F. 0, G, 0, C, 0, B, 0, A. So it looks and smells like this. It's just that it doesn't have the missing samples, D prime, E prime, F prime, G prime. It has zeros for those. So that's all X of E of n is doing in this system. It's just inserting zeros. It starts with X of n, which is this guy. It pushes them apart and it puts zeros in between the samples. Okay, now that we know how X of E of n looks like, let's try to relate the discrete time Fourier transform of X of E to the discrete time Fourier transform of X of n, and analyze this system in the frequency domain to find out how is this spectrum related to that spectrum. Remember, that was our goal. We wanted to relate the spectrum of X of I to the spectrum of X. So let's relate first the discrete time Fourier transform of X of E of n to dTFT of X of n. How would we do that? Well, just write down the expression for the dTFT of X of E of n. X of E of n, mathematically first, what is it? Well, it's given by this equation here, but we can rewrite that in the following way. You can write it as summation over k of X of k delta of n minus kl. So this function only takes on non-zero values when n is equal to 0 plus l plus 2l, 3l, or plus or minus l plus or minus 2l, etc. Right? So add those values, then the shift property holds true, and then X of E of n takes on the value of X of k at those. And because delta is 0 otherwise, then it does this thing. So this mathematically is equivalent to that. Now, what is the dTFT of that? X of E of omega. So X of E of omega, which is dTFT of X of E of n by definition, is given by what expression? Well, it's summation over n of the signal times e to the minus j omega n. What is the signal? The signal is summation over k of X of k. Let's just copy that over. Delta of n minus kl. Good. And what do we do in most situations like this? When you can't move forward anymore, you just interchange the summation. Then you get the summation from k. These are all from minus infinity to plus infinity, minus infinity to plus infinity, minus infinity to plus infinity. So the summation from k minus infinity to plus infinity, bring X of k out and put all the n dependencies in one place. And from minus infinity to plus infinity of what are the n-dependent things? There's this delta guy that's n-dependent, and then e to the minus j omega n. So it's delta of n minus kl, e to the minus j omega n. And what's this thing then? The shift property again holds true. It's e to the minus j omega kl. What's this noise? Is it somebody's cell phone? Yes? Okay. Lk. And so what you get here is x sub e of omega is summation from k minus infinity to plus infinity x of k e to the minus j omega lk. And then how is that related to the Fourier transform of x of omega? Well, let me write down the Fourier transform of x of omega as summation from k minus infinity to plus infinity of x of k e to the minus j omega k. Comparing these two things, how are these two things related to each other? It looks like if I replace all the omegas in this equation, and this side, if I replace omega with omega L, I get this guy. So x sub e of omega is nothing but x of omega, where I replace the omega with omega L. I put an arrow here so you can see replace. So x sub e of omega is just x sub omega L. So once again, it's just shrinking of an axis, changing the labels on an axis. And pictorially, how does that look like? So let me put a line around that because we spent a bunch of time deriving it. But what does that look like? If x of omega looked like this, as a function of omega, let's say it went from minus pi to plus pi. Okay. How would x sub e of omega look like? Just this is pi, this is 2 pi, this is 3 pi. Just change the label of draw the same thing, but change the label. And how do I change it? I have to scale it by L. So this point becomes pi over L. This point becomes 2 pi over L. Minus pi over L. And this point in the middle is, I'm sorry, this is 3 pi over L, and this is 2 pi over L, etc. This is 0. So this is x sub e of omega. So going back to this picture that we had earlier, this was our x of omega in the continuous time domain, continuous time Fourier transform. This was our x of omega after you sample it at rate t, and this was our x of omega after you sample it at t over L. It also went all the way to pi over L's, but then it repeated itself with period 2 pi. So comparing these two signals, this is x sub e of omega and this is x sub I of omega. I know I changed my shape of my spectrum as the day went along. If it was rectangular, it should have remained rectangular. If it was wiggly, it should have remained wiggly, but it doesn't matter. So x sub I is also the same spectrum, but going from 0 to pi over L. So how do you think I can get this guy from this guy? All I have to do is get rid of the blobs in the middle, this guy, this guy, this guy, and that guy. If I get rid of these, then x sub e would look like x sub I, right? They both have the same, they both go up to the same point, which is pi over L in this case, right? Or if you were to be, yeah. So, is that clear? Yeah. So all I have to do, and in fact we could have made this a bit more general so that it doesn't just hold for the critically sampled, it could hold for even if it's not critically sampled. This, more generally, this is omega n t over L. More generally, this is omega n t. So this point more generally is just omega n t, and this point more generally is omega n t over L. Okay, but I've drawn it for the particular case where omega n t is equal to pi. Okay, so anyway, all I have to do to go from here to here is remove this piece. I have to get rid of this piece and that piece, and then this spectrum would look like that. And so how do I do that? A low-pass filter. And what kind of a low-pass filter do I need? A low-pass filter that keeps this. That means band limited to pi over L and minus pi over L. Or more importantly, band limited to omega n t over L, or omega n t over L. Okay? So this is the low-pass filter I would have liked to have. A box-type function to keep this and to throw away those other guys. This is my h of omega, if you will. Okay? And what would be the impulse response of such an h of omega? It's a sinc function. And it would be h of n sine of pi n over L over pi n over L. Okay? So mathematically what I'm saying is obtain, so the upshot of all these drawings, could you zoom up just so you can show half of this? Okay. Zoom up just a tiny bit more. Great. So we want to obtain x sub I of n from x sub e of n by just low-pass filtering it with something that, with a low-pass filter with cutoff of pi over L. That's all we want. And that means that x sub I of n is x sub e of n convolved with h of n, where h of n is this sinc function that we wrote earlier, sine of pi n over L, pi n over L, which means that x sub I of n is summation over k of x sub e of k, h of n minus k, which we're going to plug in. X sub I of n is summation over k of x of k times sine of pi n minus kl over L over pi n minus kl over L. So I've gotten rid of x sub e of k and put in, using this expression, put in the value of x here. You see, x sub e relates to x in this way, and it's 0 for a whole lot of the values. But that's why in sine, in the sinc function here, I've replaced it with n minus kl, because it's only non-zero when this thing is integer multiples of L. So from here to here, all I'm doing is plugging in expression for x sub e of n to go from this line to that line. Is that clear? That's why these factors pop up, because of that. Yeah? I could have introduced one more step here where I change the indices and go from the ones that are this and then the ones that are not that, but I combine two steps and sort of get that one. Is this last step clear to anyone? Yeah. Okay. This thing is summation from k minus infinity to plus infinity, right? So it'll have, let's just expand it. It will have xe of 0, xe of 1, xe of 2 times. So it would have xe of 0 times h of n minus 0, xe of 1 times h of n minus 1, etc., right? But the only non-zero values of xe are 0 plus or minus L plus or minus 2L. So if I were to expand this summation, the only non-zero values I get is xe of 0 times h of n minus 0, xe of L times h of n minus L, xe of 2L times h of n minus 2L. I expand it that way, and then that results in this. Did you get it? There's a whole bunch of zeros here. That's all. Yeah.
In the frequency domain, those two curves should be multiplied, but you have only one square window.
No, I don't have one square window. H of omega, discrete time for, you're saying I missed this one?
Yeah.
No, this is 2 pi. So this thing, I only drew one period of that. Right. So that also repeats itself. Okay? Oh, I lost where I was. Okay, so is everybody convinced we get this now? Yeah? More convinced than before? I see a lot of, let me back off here. So, and as an intermediate step here, let me write it down. So x of I of n is da 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 plus xe of 0 times psi of, h of n minus 0 plus, what's xe of 1? It's 0. What's xe of 2? It's 0. The next time this xe of n is non-zero, it's xe of L. So it'll be that 0, 0 plus x sub e of L times h of n minus L plus x sub e of 2L times h of n minus 2L plus that, etc., etc. And then you rewrite that. This is the summation you get. So what does this whole expression mean? What's happening here? Yeah.
Before you go into it, how do you get x of e of n? And how would you implement it?
X of e of n is given by this expression. You just put in zeros in between x of n, just like with, let's see, where is the picture? Here's x e of n. If x of n was a, b, c, d, e, f, g, x e of n is a0, b0, c0, d0, e0, f0. Yeah?
But you know how the sync function, like, you would go past through it?
Yeah, I was going to show it in just 1 sec. Hold on one more second. If it doesn't answer your question, come back. Yeah? So how does this, let's draw that sync function just like you said. So how would xi of n look like? Let's plot this thing. So what it would be, it takes on the, let's just plot that. It's x of 0 times, let's say this is x of 0, and then it would have x of, yeah. So this expanded summation, xe of 0 is the same as x of 0. xe of L is the same as x of 1. xe of 2L is the same as x of 2, etc. So it'll be, it'll have x of 0, and then at location L, it'll have x of 1, the contribution at x of 1, and then at location 2L, we'll have contribution x of 2, etc. And then it'll have a sync function here that does like this. It's a sync function with a L type thing here. So this is minus L, and you have x of minus 1. And you have minus 2L, and have x of minus 2. So it is a sync function that does that. So the first, you know what? Let me honest to God expand this thing, because I think I did a sloppy job there. Yeah, let me just expand this real carefully. So xi of n is dot 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 plus x of e of 0 times h of n minus 0 plus x sub e of L times h of n minus L plus x sub e of 2L times h of n minus 2L plus dot 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 dot. Now x sub e of this, so it's dot 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 plus x sub e of 0 is x of 1, h of n, plus, I'm sorry, x of 0. This one is x of 1 times h of n minus L plus x of 2 times h of n minus 2L plus dot dot dot. And this thing is x I of n. If I replace h with the sinc function, then you can see that this expanded summation here corresponds to this. It's x of 0 times the sinc. This is h of n. And this is x of 1 times another sinc, but shifted by L. So it will do this. And then x of 2 times another sinc, but centered around it. Okay? So now we got what we wanted. We're getting x of 0, x of 1, x of 2. They're L samples apart. We've upsampled it by a factor of L. But you're wondering what this is that sample 0. This xi of n is a function of discrete time n. You've never seen sinks on top of discrete time n, but now you do. So this is 0, 1, 2, 3, 4. Let's say L was 4, 5, 6, 7, 8, etc. So what is the value at this point? That's the missing thing that we had shoved in a bunch of zeros. Okay, this is the zeros we filled in. I also changed the sampling rate on you. I shouldn't have. But these were the zeros that were missing. So how did we come up with these zeros? Essentially what we did is put a sinc over it in the discrete time domain. Another sinc. Yeah. That these samples that we had goes through 0. It doesn't mess up those. But in between, how do I compute the missing value of 0? It's the sum of the contribution from this sinc plus that sinc plus that sinc plus this sinc plus that sinc. All the sincs from all the way minus infinity plus infinity, they all contribute for me to compute what the missing value here, which I had initially put in 0, is going to be. Okay? Which is this picture here, but I screwed up and I made the upsampling rate 4 instead of 3. But it doesn't matter. How do I compute this, 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 and this? I got to put all my sincs and then add up all the sincs, and that gives me the values. Okay? And again, this is only going to work if initially our x of n was sampled properly, no lower than the Nyquist rate, because if it was, then this new signal we get doesn't correspond to the upsampled version of the original. Because if this wasn't sampled properly, there would be aliasing already here, and then everything will get messed up. Okay? So can I upsample? If I had a continuous time signal that I had sampled at a particular rate, and now I changed my mind and I wanted to have it at a higher sampling rate, could I easily obtain it? Yes, only if you had sampled it properly to begin with. In other words, lost no information. Okay? So that is the meaning of x of I of n, and that's the expression for it. Page 7. And that is the expression for it. It's x of k times this sinc guy. And this is the picture for it. So once again, to draw everything pictorially in the frequency domain, what is happening in the frequency domain? Here is my continuous time signal. I'm drawing everything now on one page. It goes from minus omega n to plus omega n. It's a repeat of all the plots, but in one shot. This is my x of omega after I sample it at rate t. What does it do? Scale this by t. I get omega nt minus omega nt. That's all it does. If I sample this at rate t, then all that happens in the spectrum, the label changes to nt, omega nt. And what happens to the spectrum of x sub e of omega, the intermediate thing we had? Well, it's the same thing at omega n t over L minus omega n t over L. We derive that. And then if I low pass filter it with something that's minus omega n t over L plus omega n t over L, that's my filter H. And what I get, so this was x sub e of omega, but with lots of repetition. So what this filter does, it gets rid of this one and that one, and I just get this piece, which is x sub I of omega. So then, doing that, Can you zoom out so people can see most of this page? Great. So if I do that, then I get just this piece from here, which is x sub I of omega. Goes from minus omega n t over L to plus omega n t over L. So this is as if I had sampled this original signal at t over L. Can you zoom out so that the whole thing, just a tiny bit? Great. So this is my continuous time signal going from minus omega n to plus n. I sample it, and it goes from minus omega nt to plus omega nt. Then I put the zeros in between every other sample, or I put 3 zeros in between every two samples, or whatever. And I get, the spectrum gets shifted becomes omega nt over L. I get junk here, and then I multiply by this low pass filter, or pass it through this low pass filter. I get rid of these two guys, and I keep the middle one here. And that's the final spectrum. So this is the spectrum I would have gotten if I had originally sampled this thing at t over L instead of at t. Okay? Are there any questions or comments? Yeah.
Is this how you try to get the continuous time signal from the discrete time signal? Because
You mean using sinks?
yeah.
Sure. I didn't explicitly go over that a few lectures ago, but yeah, that's you. There, exactly. Essentially, what you're doing here is you're reconstructing a continuous time signal, and then boom, sampling it at the midpoint that you should have sampled before. Right. So what he's saying is, when I put these sinks on top of each other, I'm essentially building the continuous time signal, and then I'm sampling it at the midpoint, or 3 points in the middle, or 1 point in the middle, etc. That's exactly right. The sink is essentially, implicitly, I'm doing what I said I don't want to do, which is get back the continuous time signal and resample it. But I'm doing that. By the sink guy, I'm reconstructing a continuous time signal. But reconstructing a continuous time signal, by definition, means I know it for all t's. In real life, when you do computer implementation, I only have to compute it, if I want to upsample by a factor of 2, I only have to compute this by lots of, at one point, if you will. Now, okay, are there any questions about this whole picture, this idea of upsampling, etc.? Zoom in, please. And top or bottom?
Just the right rate where it is. I can't.
This one? Minus omega nt over L plus omega nt over L. Okay. Now, having said all these things, is this a terrible... I mean, in practice, if I just gave you an image, for example, it was 100 by 100, and let's say your mom or your friend or your dad wanted to have 200 by 200 image, would you, what would be, would you go ahead and implement this? How would you do it? Would you actually have, what is the immediate, look at this picture, what's the immediate pitfall of this approach that I just described? Yeah, you have to have the sink. And what about sink? It's non-causal, it has infinite extent, right? Like for me to know what the value here is, I have to know the contribution from this sink, this sink, this sink, this sink, this sink, all the way to that room, all the way to the end of the campus. So ideally speaking, because the sink function is infinite in duration, I mean, it's not a matter of causal or not causal, it's just infinite in duration, it never ends. So to find out what the sample is doing, I got to know what the millionth sample to the right is doing. And when you have a picture, let's say I take a picture of you guys, to figure out interpolate the value of this lady sitting in pink shirt, do I have to know who's sitting in the other room? Like what Dan's signal looks like? No. So what has gone wrong? What's going on here? Hmm?
You're using an ideal low pass.
Yeah, low pass filter is
Yeah. Yeah, but more than that. Well, I think I tripped you in too many different ways. The real answer is, yeah, to find out the sample of her T-shirt at this pink value, I need to know something very, very close to it. But I really don't need to know what Dan's yellow shirt looks like. The reason is that that signal is a finite, it is not band limited. The picture that I was just talking about, anything that's a finite duration cannot be band limited, right? Finite duration in time, it's not band limited. But anyway, the answer is in real life, you truncate sinks. The sink, even though it goes on to infinity, it does die off as 1 over n. So after like 5 or 6 samples, its effect, the effect of these guys becomes negligible. And so you can get rid of it. So this is called band-limited interpolation or band-limited upsampling or something. So you inherently assume your signal is band-limited. That's why you're stuck with sinks. The word sink and the word band-limited go hand in hand. If you want to do band-limited interpolation, you are stuck with sink. Now, as a matter of practice, like if you didn't take 123 or 120, you're just like an ignorant student or something, well, how would you interpolate? You had this signal and you wanted to know that your signal went through D here and went through E here. How would you find the point in between? Well, what's a simple-minded way of doing it? Average. Yeah. That's called simple interpolation or average interpolation. If you wanted to be a little bit more sophisticated, slightly more sophisticated, then how would you do it then?
Maybe quadratic of the points.
Yeah, you take into account the neighbor as well and do some sort of quadratic. Or you do maybe bilinear interpolation, or you do bicubic interpolation, or something like that. Okay? But those are not band-limited interpolations. So what I want to emphasize is, when you talk about the word interpolation, it's very important to know what kind of interpolation you're doing. And this whole course and the 120, 123 series is overly myopic in that the band-limited assumption just comes in all the time. We start with having spectrums and things are band-limited, and then because of that, the sink thing pops up all the time. Why? You have a band-limited signal, you sample it, you want to reconstruct it, you got to put sinks. That's where sink comes in. Because sink is the inverse Fourier transform, or the impulse response of a box filter, which is a band-limiting operator. But if you step out of 120, let's say if you took a graphics course and they wanted to avoid aliasing in their texture mapping, they don't put sinks anywhere. They don't do band-limited interpolation. What they do? Bilinear interpolation or bicubic interpolation, whatever. So when you do image processing, let's say, it's even worse in 2 dimensions. I have samples of signal at these locations, and I don't want to know it exactly in between. I don't want to know these guys, the red guys. I want to know a real arbitrary point smack here in the middle. It's not integer related to anything. How do I find out what the signal does here? You can do bilinear interpolation. You know the black guys. You say, oh, it's this distance from this distance from this. I do some sort of weighted averaging. Or I can get more sophisticated, bring these samples on, or even more samples on. So in graphics to avoid aliasing that, you do something like that. In video, what you want to do is you want to take advantage of temporal redundancy across frames, and you want to interpolate the signal, at an arbitrary. You have an image that's sampled at this, but you want to do what's called fraction of a pixel interpolation. You want to know at location 1/8. This is location 0, 1. This is 1/2. This is 1/4. I want to know what does the signal look like at any 1/8 location. And by golly, doing sync interpolation will just make any video system become so slow. So people do other kinds of interpolation. So interpolation is a big topic, if you will, in all kinds of fields. And all I'm saying is what we covered in this course is called band-limited interpolation, which has got this sync that goes on forever. But conceptually, it helps you sort of understand how this thing works. I'd like to perhaps end today's lecture with just one comment, and that is changing the sampling rate by a non-integer factor. Okay. let's come back here. So changing the sampling rate by a non-integer factor. So far, I've told you if you have your signal, you can upsample it by a factor of 2 or 3. You can downsample it by a factor of 2 or 3. Those are all integer numbers. What if you had a signal and you just weren't happy at the rate that it was coming at you, and you wanted to change the sampling rate by 2/3 or 4/5 or 5/4 or 3/2 or something like that? How would you do that? Well, it's non-integer, but I'm still assuming it's a fraction. I don't want to upsample by square root of 2. That'll be difficult. You've seen in Corey elevators, between 3 and 4 there's a pi, between 2 and 3 there's an e. So that'll be for the midterm and final. You guys have to figure out how to subsample by e and pi. But for me, for the lecture, just talk about integer factors. So suppose that you wanted to change the sampling period. So the problem is change sampling period by a fraction. Okay. So how would you go about doing it? So for example, this is x of c of t, and initially you had it sampled at t, and you got x of n. But now you changed that, and you really wanted to have sampled it at t prime, where t prime is, I don't know, 1.01 t. So that's x prime of n I get. How would I get x prime from x? Well, I can cascade an upsampling and a downsampling system. I can first upsample by a factor of 100, and then I can downsample by a factor of 101. And so how would my system look like? Well, I start with this is just concatenation of the ideas we've discussed in the last few lectures. You start with x of n. How do I upsample by a factor of L? Well, this is the upsampling box we just talked about in today's lecture. Upsample by a factor of 100, or L. And then right after that, I have to have that low-pass filter with cutoff of pi over L. That's today's lecture. And how do I downsample by a factor of 101? Well, it's also, we did a bit of review of that in today's lecture. Before I downsample anything, I got to make sure there's no aliasing. So I first pass it through a low-pass filter that has cutoff of pi over m. Because if I don't, I run the danger of having aliasing. And then I get rid of the samples, downsample by a factor of m. And whatever that comes out is going to have the correct sampling rate. So for x of n, the sampling period was t. It's as if I sampled my original continuous time at c. This box is essentially make the sampling period t over L. And then by the time I come out right here, it's t m over L. Okay? So it's just concatenation of the ideas that we've talked about. Now, I must admit, in practice, nobody really from 1 to 1.01 does any of these complicated things. But if you had from 1 to from t to 2/3 of t or something, you do it 2 and 3. Now, but what's another example in practice where you want to change the sampling rate? A real practical example. The movies that are made for movies are how many frames per second? Anybody? Nobody here pirates movie. Oh, we should not talk about that. We're going to get arrested. Not on TV anyway. Well, I'm the only one on TV. They wouldn't know you answered this question. So how many frames per second are movies shot at? 24. Good. How many frames per second is TV? 30. So to change the sampling rate from 24 to 30, ideally you could do some of these things. But do we do that? No. How do we do it? Like the movies made for movie, they get all shown on TV, right? How do they go from 24 to 30? Do they put a blank? No. How'd they do it? Do they do this? No. That's the problem with me. I teach you all these things, and then at the end of the lecture, I say nobody ever does it. They do it a different way. But it's good. You have to be honest. So how'd they do it? Quick. Repeat. You got 24 frames in 1 second. They want to have 30 frames in 1 second. You got to come up with 6 frames. You go in equally spaced intervals and repeat 6 of the frames. It equals, just repeat it. That's it. Too expensive, too complicated to do any of this. But I mean, we should tell them to do this, right? Once you guys become executives in these movie companies, just tell them to do it properly. But one last comment about it. But 2/3. But that's a small thing. That's my point. From 24 to 30, it's a very small. You can get away with it, and you don't even notice it. But actually, well, maybe you do notice. But let's not dwell on that. But when you go from like 2/3, that's a pretty significant thing. You can't just repeat that. Then you really see the difference. So one last comment about this is, if you have 2 filters, two linear time invariant systems, we can sort of combine them. And so what you could do is you could say x of n coming in, upsampled by a factor of L. I get my x of e of n that we just talked about. And then I have one gigantic filter, low-pass filter. And if I cascade 2 low-pass filters, one of them is cutoff frequency of pi over L, the other one pi over m, what's the effective low-pass filter I would have had to have to replace these 2 things in a cascaded way? Pardon? Exactly. And if you multiply them, what do you get? You get another low-pass filter whose cutoff frequency is minimum of pi over Ln. So minimum of pi over L and pi over m. Cutoff is minimum of pi over L and pi over m. And then downsample, and out comes the properly T over m over O sampling. Okay, I think I'm going to stop now. We probably talked just a little bit more about multi-rate signal processing and polyphase decomposition on Friday's lecture, and then we move on to filters. So actually, just a quick show of hand. How many people in this class have taken already 126 or equivalent? And how many have not? Quite a number. Wow. Okay. All right. Thanks. Yeah, sure.
The CRT that you discussed last night, does it work